Hello, can anybody hear me? I'm sorry we're having a little technical difficulty, but if you can hear me, please send me a text message so that I know that it's working now. All right, thank you so much. I'm sorry for the delay. Sorry if you got a notification to join an hour earlier. We had a little bit of trouble today, but I think we are back on track. So it's great to see everybody joining us. Great. All right, well, thanks for joining our webinar. We're doing a last one for December, and I think everybody's probably scrambling to finish up the year strong. So we appreciate your time. And let's go ahead and get started. I just want to, I guess, introduce myself first. If you haven't been on one of my webinars yet, my name is Kelsey Noyes, and I'm with Neometrics. And a little background about me: I have a mechanical engineering degree from Minnesota, and I've been in the inspection metrology 3D world for about 20 years. So I picked a topic today to discuss with you, and it's designing for additive manufacturing. And this is our agenda for today. So I'd like to start by telling you a little bit about Neometrics. Then I'd like to review our 3D printer lineup. Then we're going to discuss some limitations of traditional manufacturing methods, supports, infill, strength requirements, and post-processing. And then what to do if you want to print a part that is larger than the printer that you have. And finally, we'll wrap up with some questions. And I'm going to try to keep this about 20-25 minutes today because, like I said, I know everybody's kind of rushing around here at the end of the year. So let's go ahead and get started. All right, so a little bit about Neometrics. So we were founded in 2003, and we've been providing 3D solutions in the Lake Mary area, but we actually have customers all throughout the country. We provide services and products. We do scanning, 3D scanning for reverse engineering applications, also inspections for quality control. We have a number of 3D printers in-house, so we definitely get a lot of service requests to print parts. We also provide professional training on both the equipment and software. The products that we have are handheld 3D scanners. We also have 3D printers, and we provide software solutions for both. All right, can people still hear me? I have one person that said they can't hear anything now, but I think the audio was working. If you can hear me, maybe just let me know. Okay. All right. Thank you for that verification. All right. So I think most of you can hear me. So let's go ahead and continue. All right. So since today we're going to be talking about 3D printers, I wanted to share with you our 3D printer lineup. We're partners with Markforged, Big Rep, and Intamsys. So I would like to spend a few minutes to talk about the different offerings that we have for each of these. All right, so first we'll start with Markforged, and this is the composite lineup. There's two size printers available. You have the desktop series and the industrial series. And if these photos are definitely not to scale, the desktop machines are smaller. The size is on the screen. It's the desktop is 12.6 by 5.2 by 6 inches. So we kind of like to say if your part can fit in a shoebox, then that's a perfect size for the desktop units. The industrial series are going to be about 2.7 times larger print volume. So 13 inches by 10.6 by 7.9. So the great material that you can print is onyx. And what that is it's a nylon thermoplastic with chopped carbon fiber. And that material can be printed with any of these printers. On the left, you have the flagship machines, the Mark II and the X7, and they can also print a large variety of reinforcement fibers that are continuous throughout your part. So Kevlar, carbon fiber, and fiberglass are some examples. And the other ones in the middle, you have Onyx Pro and the X5. Those you can use Onyx with fiberglass. And then the Onyx 1 and the X3, you can print Onyx with that. And if you want more details, I know this is just a quick run through these printers, but definitely reach out to me. I'd be happy to share some more information. All right, and this is pretty exciting news. The FX20 was just released. It is the biggest, fastest printer that Markforged has to date. It's actually about 5 times bigger than the industrial series and prints 8 times faster. So it's really impressive. The size is on the screen 10.6 inches by 15.7 by 15.7. So we're really excited about this new printer. The materials that it can print are going to be actually all flavors of the Onyx. There's also Onyx flame retardant, Onyx ESD, and then white nylon as well. And then you can also have the reinforcement fibers that I mentioned, like the carbon fiber and the Kevlar and the fiberglass. And then the really neat thing is that they're now introducing a brand new material, the Ultim 9085. This is a high performance thermoplastic, and it's often used in aerospace industries. And the really neat thing is you can also use the Ultim 9085 with reinforcement carbon fiber. So you have the advantage of your strong, stiff parts as well. So if you would like more information on this new machine, do not hesitate to reach out. All right, and then we have the Metal X system. So this is an office-friendly 3D metal printer. It actually consists of 3 components. You have the 3D printer, and then a wash station, and then the sinter oven. And there's actually quite a few materials. Stainless steel is pretty popular because it is strong and it does resist corrosion. Copper is a great choice if you have thermal or electrical conductivity requirements. Inconel 625, that's also an extremely corrosion resistant material, especially at high temperatures. And then there's also some tool steels also available, A2, D2, and H13. So we have one of these in our facility. So if you're looking for metal parts that you want printed, definitely send us files. We'd be happy to print them for you. If you want to stop by and visit us to check it out, you're always welcome to stop by. All right, if you want to print large parts, then Big Rep is ideal. The Pro unit and the One both have an impressive print volume of about 1 meter cubed, so 3 feet by 3 feet by 3 feet. They all have dual extruders and heated print beds. We actually just got a brand new Studio G2 in our office and we're loving it. Its print volume is 3 feet by 1.5 feet by 1.5 feet. So you see a variety of materials that Big Rep offers. It's also an open printer, so you can use materials from third parties as well. So again, if you have large parts or if you want the ability to print many small parts, just let us know. All right, and then finally we have the Intamsys printers. The name stands for Intelligent Additive Manufacturing Systems. So you'll see the materials offered through Intamsys in that pyramid. So they're kind of categorized. You have the biodegradable thermoplastics, general thermoplastics, the engineering thermoplastics, and then finally the high performance engineering thermoplastics like the Peak, PEC, and Ultim. These printers, they all have heated bed plates and they also have heated printer chambers. The FunMat HT is the desktop entry-level printer. That's a single extruder printer. It has a print volume of 10.2 inches cubed. And then the next one is going to be the FunMat Pro 410 that has dual extruders and a print volume of 12 by 12 by 16 inches. And then the FunMat Pro 610 HT also has dual extruders, and its print volume is 24 by 20 by 20 inches. You'll see a fourth printer is there that's called the Flex 510, and that's specifically for flexible material like TPU. So if you have applications that require that flexible material, then you'd want that one. So I would be happy to explain more details about all of these printers. So if you have any questions, just let me know. And keep in mind that we offer services. So if you'd like us to print parts from any of these machines, we are happy to do that as well. All right, so now to continue to our main topic today, designing for 3D printing. So additive manufacturing is becoming more and more popular. And it's really, a lot of it's due to the limitations of traditional manufacturing techniques. So traditional manufacturing refers to subtractive methods like CNC, laser cutting, water cutting. The diagrams on the right actually, I think, are a good summary of the difference between an additive process and a subtractive process. So in a subtractive process, you start with a large piece of material and you cut and shave away at it until you've created your desired part. And this creates a fair amount of waste. But in contrast, with 3D printing, you actually feed the filament material into the printer, which builds the part layer by layer, and it results in much less waste. Softer materials, they're easier to machine, but they also wear quickly. The traditional machining process also requires skilled labor. This directly affects turnaround time since jobs can only be completed during working hours. Where 3D printers, they can run all night during weekends and holidays. Complex geometries can also be really challenging and sometimes impossible to machine, but they can be easily 3D printed. All right, supports are often used when 3D printing, especially when printing overhangs. They help prevent part deformation. They secure the part to the print bed. They basically ensure that all the pieces are secured to the main body of the printed part. I like the analogy to scaffolding. They're needed temporarily to build the part, but then they're later removed. Features that require supports are overhangs, holes, and bridges. I think the photo on the bottom left does a really good job of illustrating when supports are needed. So features that have angles that are greater than 45 degrees, they can be created without supports. And so I think if you notice the Y, you'll see that the 45 degree angle, there's no supports needed. But then when you look over at the H, it's very clear to see that the bridge of that H needs support. Just like the T, both of the overhangs also need support. So you might want to think about if you can change some of the angles in your parts to avoid supports. Something else to consider, circles. Circles in the side of your part would require supports, but using that 45 degree idea, you can actually change the top of the circle to so basically you have a teardrop or a raindrop shape instead. So that way you can print holes without needing supports. Supports can actually be breakaway or they can be dissolved. So this might be helpful to use a dissolvable support if you have supports created in areas that might be tough to pull out. So definitely some things to consider. So what does the inside of a 3D part look like? Well, often there's an infill pattern present, and you actually have control over how much infill. So basically, this is a nice picture that shows 0 infill all the way to 100%. I'd say most 3D printed parts do have sparse infill because one of the big advantages of 3D printed parts is they're typically lightweight. But like I said, you do have the ability to customize that for each application. Most slicing softwares, they usually default somewhere between 20 to 40% infill. But some things that you might want to consider when trying to decide on the percentage is the strength critical? So if so, this might be a good reason to use 100% or solid infill. Are the walls of the part thin? If you increase the infill, this will also help with the overall strength of the part with thin walls. On the other hand, if the part needs to be lightweight, then you'll want to use sparse infill. If you have a really large part, you can often get away with sparse infill here. There's really no need to waste a bunch of excess material, and it also keeps the weight down. If you want your part fast and cheap, like perhaps with some early prototype versions, then definitely use a sparse infill. All right, so strength requirements. So there's definitely some things to consider when you're designing your part for strength. What is the part's overall function? Is there going to be loads at different areas of the part? Is it going to be throughout the part? What material would make the most sense? For example, PEC, if you need a high performance thermoplastic, if you want to, you can actually heat treat PEC later, and that increases the strength of that material. Maybe you want Pro HT because you like the biodegradable nature. Maybe you need to reinforce your part with continuous fibers. And so there's a lot of things to consider. And we actually did a webinar recently that covers selecting materials. So if you missed that, definitely go to our website and check it out. Some other things to consider are the wall thickness. So if you would like to increase strength, you might want to make your walls thicker. That would also help increase the strength. We've already talked about infill percentage. So the higher the percentage, the stronger the part. And then something else to consider is how are you going to place the part in the print bed? How are you going to set it up while it prints? Which direction are the layer lines going to go? And how does that affect strength? The picture on the bottom right has two blue brackets, and the layer line on the left side, they're running the width of the part. So if you can look closely, you can actually see they're running from left to right. Or on the right side, that bracket, the layer lines are actually running the length of the part. So looking at those two, which do you think is going to be stronger, the one on the left or the one on the right? Well, whoops, one of them broke. So it was actually the part that had the force applied with the width of the part. And it's because the layer lines are going to be weakest in between because they're just simply bonded together. But if your part, like the bracket shown where the layer lines running the length of the part, then you want to take advantage of the strength of the material by running the lines in that direction. So definitely some things to consider is part orientation and, how does it affect when you apply a load? All right, so are there some things you can do to minimize your post-processing efforts? Well, removing supports is one of the most common post-processing steps. So again, can you orientate your part in a position that maybe would give you less support? So I have an example on the screen where there's a CAD in the slicing software. So we have a part that is kind of an L shape. And if you notice on the top, when we actually slice it, it creates quite a bit of support. So another way to orientate this part is to flip it over. You want the flat side on the bed, and you'll notice it's going to require a lot less support. I also printed out the print time. So for the top, it's going to take 1.5 hours versus about an hour for the bottom, and it also costs less money. So $2.53 versus $1.44. This is a really small part, but you can imagine the savings if your part is larger. Another thing I wanted to point out was the circle versus that raindrop. So if you notice on the far right, that circle is still requiring supports. So before I actually printed this part, I would probably change that circle to the teardrop shape instead. So here's an example of a part that has some design changes to be more efficiently 3D printed. So you'll notice all the 45-degree angles and the diamond-shaped cavity throughout. So these quick changes allowed this part to be 3D printed without any supports. And the part at the bottom right, it was originally designed to require assembly because of the machining limitations. But now it can actually be printed as one complete piece. So there's no additional assembly required. So it's really nice. You can see you can have individual savings per component, or if you're going to be printing these parts throughout the year, you'll definitely benefit from an annual savings. And something else you might want to try are soluble supports. So if you have dual extruders, one of the extruders can be designated for your soluble support filament. And this will make removing supports really easy. There's water-soluble options, and there's some others that require a solvent. Like HIPS, for example, needs a limonene solution. But it's definitely something to look into. All right, so now what if the part you want to print is too large for your print bed? So I have an example on the left of a really large part. It's inside the slicing software. It's a little tough to see, but there is a little grid that you see below that's representing the print bed, and the part does not fit on it. It is too big. It's also showing me it's red, meaning that it is not going to print. So what we can do is you can cut the part in half, and you can just design a fastening mechanism, and then you can print this separately. So now each half fits very comfortably on my print bed. So you print it out, and then you finish it by just assembling those pieces together. So you might be wondering, after you print out the parts, how do you fit them together? What kind of fastening joints could you use? Well, there's actually quite a few techniques to choose from. Many are borrowed from the early woodworking days. We have the T-brindle joint as an example, or the dovetail joint. We actually use that technique a lot. I like this example of the box with the sliding dovetail top that comes nice in and out with the angled walls. You can also use a snap fit. So you can snap the part together once it's locked, and then it can lock into place. Another way is to do a rotating joint. So if you notice on the right, the part will fit in, and then if you turn it, then it won't be able to come back out. So you can lock it into place securely. All right, then you can also bolt your parts together using existing hardware. Oftentimes people will ask if you can print threads, and while you can, if the thread isn't too small, it's not always a great choice for plastic parts because the printed threads will wear very quickly. But you can purchase threaded inserts, and you can easily add them to your printed parts. There are different methods to add inserts. You can press them in or gently hammer them into place. Or some of them you can actually add mid-print, and then you can continue printing over them. Or another example are heated inserts. So what you'll need is the hardware, you'll need a soldering iron, and you definitely want to design your part for these inserts. So instead of just holes, I think it's best if you use a counterbore so that you can slide it in much easier. So once you just add that to your CAD, you can send it to the printer to print. And then you just heat up your soldering iron, and you might want to use a tweezers to hold the insert. And then you just place it in the hole, and then you just wait till it heats up, and then you can gently press it into place. It's melting the plastic a bit as it goes in so that when it cools off, it's going to be secure and it's going to be well placed and ready for you to bolt together. So here's an example of a part that's finished with all of their hardware inserted, and it's ready to use. So that definitely makes joining parts together really easy. All right, well, that pretty much concludes what I had to share with you today. So I hope you found it helpful. If you have any questions or if you have projects that you'd like to discuss with us, definitely reach out. I have my email address on there. You can also call me. That's my cell phone. And remember that we are happy to work with you if you have service prints that you'd like us to do, or if you're looking to add a printer to your location. So definitely let me know if you have any questions. Let me see if anything came in. I think there was one question I see. Is there a way to decrease your printing time? So there's a few things you can do. We talked about using less supports. So are there ways that you can print your part to use less support? You can use less infill. And also the layer height. If you have a larger layer height, your parts will print faster. So those are some tips. All right. Well, I think if there's no other questions, I promised I'd keep this short today, so you guys can get back to it. But I wish you a very happy holiday season, and we really look forward to seeing you all in the new year. So thanks again for your time, and we'll see you in 2022. Thanks.